All right, let's talk about drift velocity. So basically, what I want to study under drift velocity is current in the microscopic scale, right? So we want to look at how electrons or basically charge carriers move within a metallic conductor when a potential difference is applied across its end. So drift velocity basically refers to the average velocity of charge carriers when they are moving in an electric field, okay, or when they are moving as a result of potential difference applied across the ends of the conductor wherein the charge carriers are. Exactly. So that is what drift velocity is. So in order to look at drift velocity, we must first know what current is. Okay, current is already, you know what current is as the rate of flow of charge. Okay, so but there are two types of current that we're going to look at. There is the average current and there is the instantaneous current. Okay, it is the average current that will commonly it is steady current that will commonly define, okay, as just simply the rate of flow of charge. Okay, so but when we look at average current, we say it is the average charge over average time. Okay, the rate of flow of charge, that is what we're still talking about. So this is average current basically. This is average current. Then instantaneous current instantaneous, okay, will be the limit as the t tends to 0 of the q dt. Okay, in other words, we could basically just say that instantaneous current is going to be dq dt. Is that clear? So where the dt is very tiny interval of time and dq is very tiny amount of charge. Okay, so that's just instantaneous. I'm going to deal with instantaneous current and average current deeper in the next class. Okay, but what I want to first do in this video is to teach you how to derive the expression for drift velocity and also derive an expression for at the end of the day be able to derive Ohm's law from that expression. Alright, so we already know that this is what current is. Now, current is basically the movement of electrons. So we soon knew that it was electrons that were moving rather than positive charges. That was why conventional current is defined as the current that moves that flows from positive to negative. But I said we now know that it is electrons that actually move in the opposite direction. Now, what causes electrons to move? Now, you should know that there must be a power source which drives or provides energy for the electrons to move. Keep in mind though that power source, for example a battery, is not going to be pushing the electron. What the power source does is that it creates a potential difference, okay, such that one terminal of the battery is at a very low potential and the other end of the other terminal of the battery is at a very high potential, and because of this difference in potential, free electrons are set in motion once there is a connection to these two ends that have different potentials. Is that clear? And keep in mind that it is free electrons that actually move, okay? Free electrons are the ones that move. I'll probably link a video in the description so that you see where I explained conduction, okay? How the free electrons actually move. So free electrons are the ones that move, and they don't engage. You should know that before the connection of to that power source, free electrons are already moving. But why do we not call their motion current, or why does it not amount to current in the conductor itself? Now the reason is because they engage in random motion, and random motion of electrons or of charge carriers is not equal to current. Random motion is not equal to current. Why? Because this haphazard motion actually cancel out each other, such that the average movement of electrons within the lattice of the conductor is 0. So because of that, the velocity of the charges, the average velocity of the charges is 0. Okay, so what now happens when we connect to a metallic conductor? These guys actually gain they gain speed. Okay, they begin to move. All right, now. So when they are connected to that end, they are able to, since they are moving, we know that there is a force acting upon them, right? Due to the electric field within which they now find themselves. The electric field, first keep in mind that the electric field is given by the potential difference across the two ends per unit length of the metallic conductor. I take that again. Potential difference is going to be V over D or V over L. I'm using L specifically because it is within a metallic conductor. The electric field that is created within a metallic conductor that has a length. Is that clear? So now, also keep in mind that there is going to be a force acting. Once there is motion, it means there is an impetus, right? So the impetus here, the force here is going to be given by the electric field times the unit charge. Is that clear? The electric field times what? The unit charge. So that is F times EQ. Now recall also that the electrons, since they have a changing velocity, it means there is acceleration imparted upon them. So we therefore can tell that we can, bring in the Newton's law of motion here, Newton's second law of motion, that says that F is equal to ma. In this case, A is going to be the acceleration of the charges, with m being the mass of the charge carriers. Now, make sure you are following me because I'm going to bring in the concept of drift velocity now. So, and what is acceleration? Acceleration is speed over time, right? But this V here is going to be what we call the V sub D, which is drift velocity. V sub D, which is drift velocity. And time here, I'm going to represent it with tau. Is that clear? So here, since acceleration is velocity over time, then we know that acceleration is change in velocity over time. Then we know that this will become drift velocity of each charge carrier over tau. Now, what does tau represent? You see, my tau represents the relaxation time from collision. This is it. Relaxation time. Now, where did I bring this from? In the lattice structure of the metal. Okay, so if this is our metallic conductor, okay, so it has a cylindrical cross section, okay, circular cross section but cylindrical body, cylindrical shape. So if I take this lattice structure, the electrons that are here, or the charge carriers, electrons are charge carriers, for example, that are here, the way they move is such that they are colliding with the lattice structure of the metal itself, that is the conductor that they make up. They are colliding with those structures. So a successive an acceleration is successful rather if the acceleration we are calculating here is going to be the acceleration between any successive collision. So that is the time between the first collision and the next collision. That is the time over which we take, or we say that the body has accelerated, because that is its relaxation time from collision. The electrons are moving and they are colliding with the lattice structure of the metal. Just keep in mind, just keep up with me, you are going to understand it. They are colliding with the lattice structure of that guy, and because of that, they are gaining speed, okay? They are gaining speed. So this acceleration, therefore, is going to be the drift velocity over tau, which is the time in between any two successive collisions. All right. So this said, we also know from here, let's call this equation 1, let's call this equation 2, this equation 3, this equation 4. Now, from equation 3, okay, we know that A is also F over m. Make sense? But so this is from 3. But from 2, we know that we know that F is EQ. Therefore, A is going to be EQ over M. Is this clear? A is going to be EQ over M. If this be the case, therefore, let's call this equation 5 now. We know that acceleration is drift velocity over tau here in equation 4, and acceleration is EQ, that is electric field times unit charge times mass. Now this unit charge might be in your textbook, might be electron, okay, because they are the charge carriers. So okay, so let me write this way, E over M, okay, so they are the same, okay, just in case you see a different convention. I like to use Q, so let's continue. Acceleration is already this, and is also this. Therefore, we can equate equation 4 with 5. What is equation 4? That is, drift velocity over tau is going to be equal to EQ over M. So from here, we can generate an expression for drift velocity such that V sub D is equal to EQ times tau over M. So this is the expression for drift velocity. This is the expression for what? Drift velocity. But in fact, because we said we are looking at current in the microscopic scale, microscopically, we can generate an expression for current as well. We can generate an expression for current. So let's call this equation 6. I'm going to tell you what we'll use it for soon. This will be useful when we want to derive an expression for Ohm's law. Let's go ahead now. So we know that if this is the cross section of our wire, if this is our wire, for example, having a cylindrical shape like this, we know that the cross section is going to be like circular, almost circular, okay? And at any point, there's going to be an area over which the electrons are packed, okay? The electrons are actually packed in volume, okay? But we can, simplify this thing based on area, okay? All right, so that this A here is going to be the cross section of the wire. Cross section of the wire. All right. Now, why is this essential? It is essential because when we describe the volume, we need the area times the length, a small length of the conductor. Do you understand? So that is why we need to define the area. Okay. Another thing we now need to parameterize is the speed, which is the drift velocity of the electron, of the charge carriers. The drift velocity of the charge carriers is going to be the small distance moved in any small time interval. The small distance moved in or over any small time interval. So if that be the case, then we know that the small distance is going to be the drift velocity of each of the charge carriers times dt. Is that clear? Okay. Keep in mind I said that they are traveling in volume, right? They are moving together in volume. So that volume, we'll call it dV, all right? So that will be let's calculate the volume first, dV, because we are taking any small volume of free moving electrons, free moving charge carriers. So dV is going to be area, area times volume is length times rate times height. That will be area in this case, length times rate, times the small distance dx moved. Is that clear? So that becomes dx times dx, a times dx. Alright? This is equation, let's call this equation 7, let's call this equation 8. Now, from here, then the amount of charge in each volume, that is dq, the amount of charge in each packet of volume is going to be nq, that is number of charge carriers, times the volume itself. Is that clear? The total charge in each small volume, in each small packet of volume of electrons moving, is going to be the number of electrons moving, number of electrons. Remember this key, I said it could be electron in your own convention, times dV. So dV is this small volume, okay? So in that case, we therefore know that this dq is going to be nq. Remember that dv in equation 8 is a dx, so it becomes times a dx. Recall again that dx is v sub d dx. Then we know that dq is going to be nq a dot v sub d dt, rather v sub d dt, keeping in mind that dx is v sub d dt. So from here, if that be the case, we therefore know that our dq is nqa v sub d dt. Now from here, we can generate an expression for current, remembering that we said that average current is dq dt, isn't it? If that be the case, therefore, we should recall that current is dq dt. So if current is dq dt, then dq is equal to I dt. If this be the case, then we know that I dt, we can substitute into this equation. This is equation 9 now. We can substitute into equation 9 by saying that I dt, which is now dq, is equal to nqa v sub d dt. nqa v sub d dt. Alright, so from here, we can divide both sides by dt. So dt takes care of dt. Then I therefore becomes nqa v sub d. Alright, so this will now be the expression for current in the microscopic scale. That is, I is equal to N. In your convention, it could be E that the Q represents. So it will be N E A V sub D. Okay? Where V sub D is the drift velocity. I'm intentionally putting V sub D here because when I write V for volume, so that you will not confuse it with V for voltage and V for distance. Some people might be saying there are too many V's there. Alright, so from here, I therefore know that V sub D, which is the drift velocity, is going to be I over NEA. Is this clear? Let this be equation 10. So from equation 10, we can now proceed forward. You know why? Because there are many more things we cannot do about this. I like to retain my Q convention, okay? I like to retain my Q convention. So from here, I can recall that from equation 10, that V sub D is equal to I over NQA. Alright? I over NQA. And recall that the same drift velocity, let's call this equation 11, that the same V sub D we got to be EQ tau over M. Alright? So we can now equate both of them. Alright? So that I over NQA is equal to EQ tau over M. Then from here, we can obtain an expression for this guy, for I, such that current therefore becomes EQ tau, okay, multiplied by NQA all divided by M, so that I equal to EQ squared tau N. No, let's do it this way. N first before Q. EQ, no, let's do it this way. NQ squared, then E tau A over M. Alright? Alright. So if this be the case, then we recall also from equation, I can't remember, that this equation 1, that E is equal to V per L, right? V over L. So if that be the case, we can substitute in here. Let this be equation 12. that I is equal to nq squared dot v over L dot tau dot A dot 1 over n. I hope you understand what I did there. Okay, so if that be the case, our current therefore is equal to nq squared v tau A over ml. All right, you can already see that we have been able to bring in voltage here and parameters that are associated with resistance. Okay, so from here I can rearrange this my expression. I can rearrange this my expression. I can rearrange this my expression. Drift velocity. If I rearrange the expression, I'm going to have I equal to nq squared tau A, okay, over ml times v multiplied by v. Okay, I brought out this v because it's voltage. And what does Ohm's law say? Recall that Ohm's law states that the voltage is direct proportional to what? To the current. Given that physical conditions such as temperature and all other things, other physical conditions are kept constant. So we now know that V is actually equal to IR, where R tends to be like a constant because it's intrinsic for a particular metallic conductor. So every metallic conductor has a degree of resistance. Every metallic conductor has its own degree of resistance. So, but what changes is with the resistance kept constant, the voltage is direct proportional to what? To the current. So if that's the case, then I can bring in something here. If I were to rewrite I will be equal to what here? V over R. If that be the case, therefore, then we know from here that I will be equal to this whole expression is going to be a constant. It's going to work like a constant. Is that clear? Such that we have V. This expression here is V multiplied by, I mean to say that R is actually the inverse of this expression. Okay? So what I want to do is, let's say I wanted to write this expression in terms of Ohm's law, that V equal to IR. Then it means that what I need here is that V from here will be equal to I ml over nq squared tau A. So this whole thing is going to be a resistance such that V therefore equal to IR, wherein we know that R is equal to ml over nq squared tau A. Is that clear? So this is the expression for resistance because there are physical conditions that are usually associated with the conductor itself. All of them. Do you understand now? All right. So like I said, remember that, if I wanted to define my parameters again, remember, M is the mass of the charge carriers, L is the length of the conductor, N is number of charge carrier, then Q or E squared is the charge carrier themselves, then tau is their distance between the successive collision, and A is the cross-sectional area of the conductor. Exactly. These are the things that all sum up to the resistance of the guy. So that is how to prove Ohm's law using that. Another thing to also do, I can also do is this. Recalling that resistance is actually equal to resistivity times L over A. If this law holds, then we can already isolate this. Okay? You know this, for any given metallic conductor, the resistance of that metallic conductor is going to be the resistivity times L over A. If that be the case, then I know that R will be equal to, that my rho is actually equal to M over NQ squared tau. Okay? so that R equal to rho L over A from this formula that I just showed you. Do you understand now? Such that this is resistivity. And you know resistivity is also intrinsic to a metallic conductor. Alright? The higher the resistivity, the lower the conductivity of the conductor, because they are inversely proportional. Alright, so this will be it for the video. Do want to subscribe to the channel and share the video with your friends. God bless you.